Hi, everyone. Welcome to a new EBI seminar series. This semester's theme, Biomass to Breakthrough, brings together leading researchers to show how biology, chemistry, and engineering can turn renewable feedstocks into fuels, plastics, and energy. From hydrothermal liquefaction to microbial engineering, we'll dive into the science, economics, and real-world applications of biomass conversion. We're kicking off with Professor Yuanhui Zhang, founder professor in agricultural and biological engineering at the University of Illinois Urbana-Champaign, who will share how hydrothermal liquefaction can transform everyday biowaste into renewable energy and its potential to shape a sustainable future. Hi, Professor Zhang. Thank you for joining us today. To begin, we'd love to dive deeper into your research on the E2E paradigm. Can you explain what it is and what it represents?
E2E stands for Environment Enhancing Energy. I want to explain the enhancing parts because in my case, we are primarily dealing with the bio-waste. It's a part of the biomass because we convert the bio-waste into something value-added product. So in a way, it not only improves, eliminates the harmful materials and pollute the environment, but we are actually enhance the environment during the process. That's what the word enhancing stand for.
So, HTL, or hydrothermal liquefaction, is at the core of this process. Can you briefly explain what that is, what HCl is, and how it fits into the E2E paradigm?
Hydrothermal liquefaction is a thermochemical processes. You put the biomass, in my case specifically, it's a wet bio-waste streams like food waste or algal bloom or the sewage sludge, etc. But the hydrothermal liquefaction is really mimic the Mother Nature's processes and make those feedstocks in a reactor subjected to high temperature and high pressure. Then we got the bio-crude oil. In Mother Nature going through the same processes, but through millions of years. So in this case, we only have about a half an hour. Then we got the similar quality of the bio-crude oil as the natural petroleum oil.
So, the result of this process is a biocrude oil product. Is this product any different from conventional crude oil?
It is similar. By the nature, they are belong to the similar processes and from the similar feedstocks like algae or other biomass or wood. So, but the process through these hydrothermal liquefaction reactors, the biocrude oil we obtained is not as good quality as the natural petroleum we got, like Texas crude or Saudi Arabia sweet crude. Our cases is a short time and a very complicated bio feedstocks like food waste or algal bloom or sewage. So therefore, the biocrude contains lots of impurities like ash, nitrogen containing compound, salt, metals, etc. So we need to do an array of the pretreatment, or in a simple word, cleanups, make it pretty much the same as the natural petroleum.
And what are some of the technologies and systems that are needed to make this work?
We have two processes. The first is the HTL, hydrothermal liquefaction, right? After the hydrothermal liquefaction, the rest of our job is to do the upgrading, more like our oil refineries. So that's the part of the research right now my group is also doing. We're doing two parts. One is to use these HTL processes to obtain biocrude oil. Then we take the biocrude oil, do the pretreatment and the final upgrading to obtain transportation fuels, including SAF, sustainable aviation fuels, diesels, and other biochemicals for potentially like for plastics and other materials. So my efforts, my lab's efforts is HTO itself So we focus on lots of efforts on the reactor designs and the processes, which is chemical and chemical engineering. So we want to improve the efficiency of the processes. Then that involves lots of chemistry, chemical engineering, and the process parameter controls, like control the temperatures, pressures. We called it we called it intensity factors. Okay. So in terms of challenge, there are lots of challenges. In general, there's some mechanical challenge, material challenge because this process high temperature, high pressure, and very corrosive, and also chemical per se issue dealing with complicated compounds and the chemical reaction, different reactions. So there are areas of the technical challenges we have to overcome.
So once the technology is in place, the question becomes what goes in it? What kinds of waste materials can your system use? Is it agricultural, municipal, or even human and animal waste?
Generally, any kind of bio waste, it should work. But so far, it works best for those we so-called wet bio waste, not so good for the lignocellulose. When we see the wet bio waste is containing a mixture of lipid, protein, and carbohydrate. So the good examples is food waste, algal bloom, algae, and sewage sludge. Those are containing a mixture of the lipids, proteins, and the carbohydrate. So those are all are good feedstocks for these processes.
It's really interesting that you can use like really any kind of bio waste. But what are some of the challenges that come with scaling this to industry?
Scale up and then eventually commercialize this. Aside some technical challenges I just mentioned, the mechanical, chemical, process, and feedstocks availabilities. And there are also other challenges. I mean, right now we are working on the technical challenges for my lab as engineering programs. We are dealing with the reactor designs and the process optimization and process controls and the value-added product development. So, but ultimately, it's going to be an economic challenge. And as long as the fossil fuels, petroleum is cheap, it's itself is a challenge for this kind of technologies to be competitive. And the industry, ultimately, they want to be profitable, right? Otherwise, they need a lot of subsidies from government. So the other thing is the government policies. If we make effort, even support this kind of research, we could make those things work faster or better, but that takes time. So challenge comes from different directions. It's technical engineering and also competition with the existing energy structures like petroleum and also from government policies. Eventually, it's also for the general public acceptance. And I think that's as long as it makes money, it's available. I think general public acceptance should not be a problem. Everybody allowed to reuse the waste stream and protect our environment, right?
With that in mind, though, do you see this technology becoming more common in waste treatment facilities within the next decade?
Yes and no. Yes, it should be popular and it will be. Eventually, our petroleum or fossil fuels need to be replaced by some renewable sources, which our HTL is exactly doing that to use the renewable, especially bio waste streams and convert it into the bio crude oil to supplement or even replace the existing fossil fuels. So that's the yes part. It's the right thing to do. The not sure part, I will not say no, but not sure part the next decade. I hope so. It depends on how much of effort we put in it. And on the other hand, we are making really good progress. And now, in my lab, we already get into the pilot scale. So next stage will be industry join the effort and scale it up and make the commercial trial on it.
And finally, bringing us to the bigger picture, if the E2E paradigm were implemented widely, what kind of environmental impact do you think it could have?
The impact will be huge. First, this whole process, we are taking the waste streams, whether it's food waste or wastewater sewage sludge or algal bloom, all those things, we already spent a lot of money to mitigate those problems. We pay for dumping fees, we pay for wastewater treatment plant fees. That's a lot of money already we put in. Now, if we recover those waste stream into value-added products, including fuels and other chemicals, so that's economically, this makes sense. Especially makes sense for a circular bioeconomy point of view. We basically convert the waste stream into value-added product. Okay, and during this process, we can decarbonize the waste stream. Before, it's all those wastes turn into the CO2 and emitted to the atmosphere and negatively affect the climate change. And then the others is seeped into water streams and pollute our water system. So it's a great deal for improving the environment. This HTO is exactly doing that to improve our environment. So in the long run, I think this holds great potential. Is again, like we discussed before, depending on many other factors right now. We have lots of technical engineering hurdles to overcome, and we need to be competitive with the petroleum. And we also need to develop the new product from this new kind of biocrude oil. But in the long run, this again holds great potentials to protect our environment or even improve our environment and makes our economy truly circular. You know, whenever we talk about the circular economy or the sustainability, the big missing link here is how do we recover the resources from waste streams? And the HTO is exactly doing this job to recover the resources and make it reused from a waste stream.
Well, Professor Zhang, thank you so much for taking the time to speak with us today. Your insights into HDL and the E2E paradigm have been incredibly valuable, and we truly appreciate your work, and we really look forward to seeing how this technology will continue to grow.
Thank you. The future is promising,
Future is
and
promising.
we also it's only works for our future generations. This needs a long-term effort.
Thank you for tuning in to the Biomass to Breakthrough seminar series, where we explore how renewable feedstocks can be transformed into fuels, plastics, and other sustainable products. If you enjoyed the session, be sure to like and subscribe for more content on biomass conversion and the clean energy transition. You can also catch up on previous talks or follow us on social media, all linked in the description below. Thanks for watching, and we'll see you next time.